Hello, my name is Øyvind Brandstad-Verbakken. I'm a doctoral candidate at the Delft University of Technology, and I am DC2 in the HEAT4ENERGY project. The overall goal of this project is to develop conversion of heat to electrical energy. A lot of the energy we put into modern industrial processes escapes as so-called waste heat. Waste in the sense that there is a surplus of heat that is often not used for anything but let out the window or the chimney. Generating mechanical energy from heat by boiling water to drive steam engines was harnessed by humans already 300 years ago. Central to the physics of a steam engine is the phase change of liquid water to water vapor upon heating. The pressure from the steam pushes on a piston to drive mechanical motion in, for example, a locomotive. The challenge tackled by the HEAT4ENERGY project is to generate electrical energy from low-grade waste heat. That is, heat from sources not hot enough to vaporize water. We will develop thermomagnetic generators for this purpose. Somewhat analogous to water changing phase in steam power, we will make use of the change of the magnetic phase of materials in a thermomagnetic cycle to generate electricity from heat. The bulk magnetization of a material is a result of the many small contributions from the structure of electrons within. When the temperature of magnetic material is below a critical temperature, there is not too much motion in the electronic structure, and the material can be in a magnetically ordered state, where the many small contributions from the electrons add up to a relatively big bulk magnetization. When the temperature exceeds the critical temperature, the motion in the structure can cause the material to be in a magnetic disordered state, where the many small magnetic contributions are scrambled in a way that does not simply add up. The change in magnetization of the material causes a change in the magnetic field in the nearby region. This change in the magnetic field can induce motion in electrons in the nearby circuit, which is the electricity we can make use of. But electrons also play a role in other properties of a material. Thus, the change in magnetic properties may be tied to other changes in the material in a desired or an undesired way. As an example, the change of the magnetic phase may be tied to the change of the shape of the structural unit cell. This instability in the structure may lead to a rapid change in the overall magnetization, which can be nice for generating electrical energy, but can be a challenge for the longevity of the material in operation. My role in the project is concerned with microscopic characterization of thermomagnetic materials. For microscopic characterization of materials, you need microscopical probes. Often this involves techniques based on radiation, such as X-rays, neutrons, and electrons. There are a few reasons why this is handy. The incident beams of radiations can, through filters and optics, be focused into small probes, suitable for small targets. The behavior of the radiation can be modeled both as small particles and as waves of energy. This wave-like nature enables spectroscopies for exploring energy landscapes within the materials and diffraction patterns, revealing the fundamental structures of the materials. These probes may also be polarized to interact directly with the magnetic moments in the material and not only the general structure. Knowledge on the correlations between the magnetic properties of the thermomagnetic materials and other properties is important for developing new and better performing materials. It is also important for selection of existing materials well suited for specific applications and for the design of future thermomagnetic devices with the strengths and weaknesses of the materials in mind. Thank you for watching. Check out the official webpage heat4energy.eu or find the HEAT4ENERGY page on LinkedIn to stay updated on this project.